Welcome to CSC 201, Lesson 3.4, Arguments with Quantified Statements. The rule of universal instantiation says that if a property is true of everything in a set, then it is true of any particular thing in the set, any particular instance. So the root word of instantiation is instance. So if it's true for all things, it's true for any particular instance. So an example of this kind of argument would say that all men are mortal, Socrates is a man, therefore Socrates is mortal. So this is a particular thing in the set of all men. So the thing that applies to all men must apply to that particular thing. So here's another example. For every real number x and for all integers m and n, when you do x to the m times x to the n, you get x to the m plus n. So this is a universal rule for all real numbers x and integers m and n. And if we choose x to be pi, m to be 3, and n to be 5, x is a real number, m and n are both integers, so we can write a particular instance of this rule that pi cubed times pi to the 5th equals pi to the 8th. Now recall that modus ponens is a valid argument of the form if P then Q, P therefore Q. Universal modus ponens is another valid argument type, and it says that for all x, if P of x then Q of x, P of A for a particular A, therefore Q of A. Let's use this argument type to write a valid conclusion for each of the following two arguments. If an integer is even, then its square is even. 2 is an even integer, therefore 2 squared, which is 4, is even. And if T is any right triangle with hypotenuse C and legs A and B, then C squared equals A squared plus B squared. The triangle shown below is a right triangle with both legs equal to 1 and a hypotenuse C. Therefore, C squared equals 1 squared plus 1 squared, which is really all we can conclude. And then we could use a little algebra after and say, thus, C equals square root 2. All right, recall that modus tollens is a valid argument of the form if P then Q, not Q, therefore not P. It uses the contrapositive of the if P then Q. So if P then Q, not Q, therefore not P. So let's use universal modus tollens to create another valid argument type. It says, for all x, if P of x then Q of x, not Q of A for a particular A, therefore not P of A. Use universal modus tollens to write a valid conclusion to each of the following arguments. All human beings are mortal. Zeus is not mortal, therefore that's the not Q, so therefore not P. Zeus is not human. All professors are absent-minded. Tom is not absent-minded, therefore Tom is not a professor. Recall that an argument is considered valid if and only if the truth of its premises implies the truth of its conclusion. That is, if the premises are true, then its conclusion must also be true. An argument is considered sound if and only if it is both valid and its premises are true. A useful tool to test an argument for validity, just the validity part, is a Venn diagram. So let's use some Venn diagrams to write valid conclusions to some arguments. So I have all integers are rational numbers. Pi is not a rational number, therefore we can use universal modus tollens to answer this right away, we would say pi is not an integer, but a Venn diagram can be really helpful. So if I use this first sentence to create a Venn diagram, all integers are rational numbers. I can make a circle that represents rational numbers, which we label Q. Q is for rational numbers. Integers are all rational numbers. All integers are rational numbers. So I can put the integers fully inside the rationals. And then pi is not a rational number. It means that pi is out here, outside of the circle of rational numbers. So quite clearly from the picture, pi is not an integer. Okay, here's another example. All flowers are plants. So I have a circle for plants. Flowers is completely contained within the realm of plants. A rose is a flower, so I can put a rose in here. So if rose lives within the flowers circle, it has to also live within the plants circle. So roses are plants. All right, let's use a Venn diagram to show the invalidity of an argument. So all humans are mortal. So I have a circle for mortals. All humans are mortal, so humans belongs within the realm of mortals. Felix is mortal. Okay, so if I wanted to put Felix in the mortal circle, it could go here or it could go here. It is unclear, right? So does Felix could be here or it could be here. So this tells us nothing about whether or not Felix is a human being. So this is definitely an invalid argument. All right, so the example we just did about humans and mortals and Felix, is it an example of converse error or inverse error? So I'm going to write it out formally. That should help us decide. So I'm going to say for all x, if x is human, then x is mortal. Okay, so that's just a translation of all humans are mortal. Then we said Felix is mortal, right? So we are assuming X is mortal. Okay, so Felix is mortal. Mortal, therefore Felix is human. It's sort of like reading the implication backwards, right? So we said, well, Felix is mortal, then Felix is human. So that's the reverse of this conditional, which is the converse. It's the converse of that conditional. So this is converse error. All right, let's use a Venn diagram to test the following argument for validity. No polynomial functions have horizontal asymptotes. Okay, so if I make a circle for polynomials, okay, and there's some other circle for functions that have horizontal asymptotes. HA stands for horizontal asymptotes. This function, some particular function, has a horizontal asymptote. This function has a horizontal asymptote. Therefore, this function is not a polynomial function. This is completely valid, right? If you live in here, you can't live in here. So, valid argument. Recall that transitivity is a valid argument that has the form P implies Q and Q implies R. P is true, therefore R is true. So it's transitive. If P, then Q, and if Q, then R. So if you know P is true, then you can go through the chain, the transitivity chain, and end up with R is true. So there's a analogous rule for universal transitivity, and we're going to use it to reorder these premises to show that the conclusion follows as a valid consequence from the premises. So first, I think it's going to be helpful to rewrite all of these as universal conditional statements. So all computer science students are clever. I would rewrite that as for all students X, if X is a CS student, X is clever. All right, the next statement says that if a student gets good grades, then they will get a good job. Okay, so for all students X, if X gets good grades, X gets good job. Okay. And then the third one says that if a student does not get good grades, then they are not clever. So we would say for all students X, if X does not get good grades, then X is not clever. Okay, and then finally the conclusion says, therefore, all computer science students will get a good job. So translate that, it says, for all students X, if X is a CS student, then X gets a good job. Okay, so all I've done is translate these into more formal language. Now I want to create a transitive chain, right? Where I have if P then Q, if Q then R, and then you know the first thing and you can conclude the last thing. So if my therefore is if X is a CS student, then X gets a good job. So I starting with P and finishing with R. So this should be my first premise. So X is a CS student should be premise 1. Okay. And then I have to end with X gets a good job. This is final conclusion. Okay. So my first premise is that X is a CS student. So this has to be number 1 here. For all students X, if X is a CS student, I forgot the word then X is clever, then X gets a good job. Okay. So my first premise is going to be if X is a CS student, then X is clever. My next premise, I now know X is clever, so I've concluded X is clever. So I need my next statement to say if X is clever, right? So it's not this one. This has nothing about cleverness in it, but this one has cleverness in it, but I want it to be if the student's clever, and here cleverness is in the then part. So I'm going to use the contrapositive to switch this around. So I'm going to rewrite this as for all students X, if X is clever, so this is the not Q, then not P, so X gets good grades. Now that's a good option for my second statement. Okay, so I have, if X is a CS student, then X is clever. If X is clever, then X gets good grades. And then my next statement, my next premise is, if X gets good grades, then X gets a good job. So I've now created a chain of reasoning, a chain of P implies Q, Q implies R implies S, and I can make my final conclusion. So if X is a CS student, then X is clever. If X is clever, then X gets good grades. If X gets good grades, then X gets a good job. Therefore, if X is a CS student, then X gets a good job.